So a set is a unordered collection collection of distinct elements. Unordered collection of distinct elements. Distinct elements. When I was working in an office, I used to work on Java, and there was a interface or parent class called as collection. There's something to do with sets. So even if you give the repeated values, when you call that class, which is basically a set, it will return the elements with unique values. Means even if you give the set values to be 1, 2, 3, 3, if you give, let's say, a is equal to 1, 2, 3, 3, 4, right? So even then, when you, it will return a to b, it will always return a to b 1, 2, and 3, 1, 2, 3, and 4. So even if any element is coming more than once in set, we are only dealing with distinct elements. So duplicates are not allowed. Duplicates are just ignored. Okay. So cardinality of A. What is cardinality of a set? Cardinality of the set is number of elements in the set. So cardinality of A is cardinality is represented like this. So this means cardinality of the set, which is equal to number of elements in the set. So cardinality of A is 4. Okay, cardinality of A is 4. And what are the elements of A? 1 is an element, 1 belongs to A, 2 belongs to A, 3 belongs to A, and 4 belongs to A. So because these are 4 elements, so cardinality is 4. Okay. So let's take only 1, 2, 3, 4. Let's take 1, 2, 3. Set is an unordered collection. Unordered collection. So we are just concerned with this distinct elements. So any other set, let's say if I take another set, any set with the same elements, 1, 2, 3 only, B is 3, 2, 1, and any other set, C is 2, 1, and 3. Then all of these are equal sets mutually. A is equal to B, A is equal to C, B is equal to C, B is equal to A. So I was talking about that class in Java, which is a set. So what happens is every time that you call a set, it will return the elements, same elements, but their order may not be same. Every time the set is called, then what it returns is a set with same elements, but the order can be changed because order is irrelevant. We are not concerned with the order in which we are collecting the elements, like what element is to be collected first, or what is second element, what is third element. So instead, we don't talk like that. That what is the first element of a set, what is the second element of a set. It's just what are the elements of set. This is not an array. Array is an ordered collection of okay, later on, but array is an ordered collection of similar data types. Leave it. So all of these elements are same. A is equal to B. So this is about the equality of two sets. Two sets are equal if their elements are same. If they have same elements, then both sets are equal. What is a subset of a set? What is a subset? So we are concerned with set A right now. So what is a subset of set A? If there is any other set whose elements are from set A, what does it mean? It means that a set B is said to be a subset of set A. A set B is said to be a subset of set A if all the elements of B, all the elements of B is also an element of A. Is also an element of A. So take two sets. B is equal to 2, 3, and C is equal to 3, 5. Now out of these two sets, B is the subset of A, but C is not a subset of A. B is a subset of A and C is not a subset. C is not a subset of A. Why? Because all the elements of B, which is 2 and 3, all of the elements of B is also in A, or the elements of B are from set A only. But elements of C are not from set A alone, because C contains 5, which is not an element of A. So 5 belongs to C. This is the symbol to represent. So on this side, this is the element. Okay, and this is your set. So belong symbol means that this element belongs to this set, or this is the element of this set. So 5 belongs to C. Okay. But 5 does not belongs to A. So there is at least one element in C that is not from A. So C is not a subset of A. Okay. If a set is given to you and you are asked to form a subset from this set, so you know that the elements for a subset has to come from A only. Has to come from A only. And from the definition of a subset, the set A is a subset of itself. From the definition of subset, if all the elements of B, if all the elements of B is also an element of A, so definitely all the elements of A is an element of A. So every set is a subset of itself. Every set is a subset of itself. So every set is a subset of itself. Now, how do you form a subset? If a set is given to you, like A is given to me, and if I have to form a subset of A, how can I do that? So it is clear that the elements of that subset is going to come from A only. Is going to come from A only. So how can we form a subset? For every element, I have two choices. That in my subset, whether I will include this element or not. I may in my subset, I may include one or I may not include one. Okay, let's say I don't include one, but I include 2 and 3. Then this is what that subset is. So you can say that B is formed. How B is formed? Because I had two choices for every element. If I choose all of the element, then I get the set itself. And that is what it is. Every set is a subset of itself. I don't choose one. Every element has two choices. So for one, I am not choosing it to be a part of my subset. But other elements, 2 and 3, is a part of my subset. So B is a set which happens to be a subset of A. So let me write all possible subsets of A. So elements of A is 1, 2, 3. Okay. Now I know one of the subset is the set itself, and that is when we choose all of the element to be an element in my subset. If I choose every element of A to be an element of my subset, then what we get is this set 1, 2, and 3, and this is nothing but the set itself. So this is one of the subset. This is trivial subset. One of the trivial subset of a set is the set itself. That is when we choose every element to be in my subset, to be an element in my subset. Now let me choose the elements. Let me choose the subsets of cardinality 2. So the cardinality of the subset is going to be from 0 to 3. The length, the cardinality of A is 3, and my subset, the elements of my subset can be from set A only. So the maximum length of my subset will be 3. That is when the subset is the set itself. And for any other subset, what I'm going to do, either I'm going to pick 2 elements and not pick 1 element, or I'm going to pick 1 element or not pick 2 elements, or I'm going to not pick any of the element, because for every element I have 2 choices. So let me write possible subsets of cardinality 2. So for cardinality 2, for every combination, so if for every combination I am getting 1 subset. So let's say for cardinality 2, I have to select 2 elements in my set. I have to select 2 elements in my set, right? Let's say I don't select 1. If I don't select 1, and then I will select 2 and 3, and this set is 2, 3. Similarly, one another possibility is that I don't select 2. If I don't select 2, then my set, I get another subset which is 1 and 3. So as you can see, to form a subset, for every element of A, you have 2 choices. Either this element is in your subset, or this element is not in your subset. And because of this, you are getting different combination. In this combination, all 1, 2, 3 is in your subset. In this combination, 1 is not in your subset, 2 and 3 is in your subset. So in this way, how many combinations you will get? This is very much like 1, 2, 3 is very much like Boolean table with 3 Boolean variables, and every variable can take value 0 or 1. So number of combinations possible is going to be 2 power 3. So here it is number of subsets possible for this set A is going to be 2 to the power 3. This time I will choose 1 and 2, and I will not choose 3. So my subset is 1 and 2. So these are all the subsets of cardinality 2. Now I will choose all possible subsets of cardinality 1. How can we do that? So for 2 elements, I'm not going to make it a part of my subset, and for 1 element, I'm going to put it in my subset. So in how many ways can you make the cardinality 1? So every time I'm just going to select 1. So let me select 1, then 2 and 3 I'm not selecting. I'm not selecting it to be my to be an element in my subset. So this is my subset. Then I'm selecting 2. Then I'm selecting 3. Now there is one more type of set. Okay, I've not discussed the types of sets, but there's one type of set which is called as empty set. Empty set is okay. How a set is represented? A set is represented by curly braces with elements, with all the elements separated by commas. So the elements of A is 1, 2, and 3. So it is enclosed between the elements of the set is enclosed between 2 curly braces, and they are separated by commas. So if a set does not have any element, then you write it like this. What does it mean? That this is a set. No doubt this is a set, but it has no element. Okay, that's what a empty set is. A set, it is a set, but no element. And it is also can be it is also represented as phi. So what phi is? Phi is equal to empty set. So one of the possible combination is that you don't select any of the element to be in your subset. So and that is your phi or this. So total number of subsets of set A is 8. There are 8 total subsets. These two, this and this, they are called trivial subsets. For every set, the set itself and the empty set, they are the trivial subsets of a set. Empty set is a subset of any set. Okay. For any given set, the set and the empty set, these two are trivial subsets of a set. Trivial subset. And remaining, so these two are trivial and remaining are subsets. One more thing, there is something called as proper subset. So what is a proper subset? Proper subset is a subset of set that is not the set itself. Or in a proper subset, you have the cardinality of proper subset has to be less than the cardinality of the set, or there is at least one element, and this is the real definition. A proper set subset of a set is when there is at least one element in the set which is not there in subset. So apart from this, for every other subset, then you can find at least one element which is in A but not in the subset. Like for this example, one is not a part of the subset, or one is two is not for this subset, three is not in this subset, two and three is not present in this subset, one and three is not present in this subset, one and two is not present in this subset. None of the element is present in this subset. So all of these subsets are proper subset. And for proper subset, how do we represent proper subset? Uh, for example, let's say this is my set B. B is equal to 2 and 3. Then uh, how do I represent that this is a proper subset? The symbol for proper subset is this, so that B is a proper subset of A. Okay, so it is also a subset. So you can write, let's say if this is C, then you can write C is a subset of A, but C is also a subset of A. This is true also, and this is true also. Okay, but in this case, this is only a subset of A. This is only a subset of A. This 1, 2, 3, this is not a proper subset. This is not a proper subset, but this is a subset. Okay, so as you can see that for a given set of length 3, the total number of subsets possible is 8. If the size of the set is n, if the cardinality of the set is n, then what is the total number of subsets possible? It is going to be 2 to the power n, because then how many combinations are possible? 2 to the power n. Okay. So if the cardinality of A is n, the number of possible subsets of A, number of possible subsets of A is equal to 2 to the power n. What is power set of A? What is a power set of A? Power set is a set of all the subsets of A. All the subsets of A. So what is the power set of A? power set of A is going to be equal to all of this. Means power set of A, in the power set, each element is a set. So set can have a set as an element. So it is possible. It means, of course, just it has to be distinct element. Set can have anything in as its element, anything. So not numbers, like in the introductory video. Student one is a set, is can be one element. Student two can be another element in a set of students. What is the power set of A? Power set of A is 1, 2, 3, 2, 3, 1, 3, 1, 2, 1, 2, 3, and 5. So this set is a power set of A. So if the cardinality of A is n, then what is the cardinality of power set of A? If cardinality of A is n, then what is the cardinality of the power set of A? This is equal to 2 to the power n. Because there are 2 to the power n elements. There are 2 to the power n subsets of a set. So each subset is an element of power set. So the cardinality of power set is 2 to the power n. This is trivial subset. This is trivial subset. Now you can say that this is one of the representation of set. This is how one of the way to represent a set is you have a curly braces and that encompasses all the elements which are separated by commas. There's another representation of set. You can represent set using a statement of English language that is called set builder notation. So that statement itself encompasses all the elements, all the possible elements. How? For example, in this case, A is equal to 1, 2, 3. I can write in English statement something like A is equal to X such that X belongs to natural number and X is less than 4. Then this is nothing but this. This n is also a set of natural numbers. N is set of natural numbers. So this is the example where number of elements is 3. But there are the sets can be finite set or it can be an infinite set. Some of the very popular infinite set, one of them is natural number, set of natural number. So which is n is set of natural numbers. Similarly, z set of all integers, q set of all rational numbers, r set of all real numbers. These are some of the popular infinite sets. Okay, what is the significance of set and subset? What is the significance of it? All of the subsets of this set A are nothing but set in themselves. They are the elements has to be decided from A. So it's like the world of A. So it is, in other way, you can understand this as that in the world of A, these are all possible sets that can be. In the world of A, this is the all possible sets that can be. For example, take the case of university. In university, you can have one set of students. Some students may be learning physics. Some students may have opt to learn chemistry. Some may have opt to learn mathematics. Some may have opt to learn about politics. Okay, so every set. So all the other sets, means a student who learn physics, they are going to be, the elements of these sets are going to be from the elements of set of students only. So set of students is like a universal set. and every other set in the context of university is a subset to this universal set. So likewise, in this case, A is a universal set. So universal set, A is a universal set, and every other set in the world of A, every other set is a subset to this A, because every other set, the elements will come from A only. Similarly, in case of university, for every other set, like physics students, sets of chemistry students, set of politics students, set of English students, their elements are going to come from set of students only. Now, it might happen that let's say there is one subject where every student is learning that subject. For example, English literature. Everyone is learning that English language. Then, in this case, this subset is the set itself. Like this is the scenario of this. That every set is a subset of itself. Similarly, there must be some subject where teachers just come to the classroom, but there is no one because nobody has opted to study that subject. Teachers just getting the salary, and the classroom is vacant. What can that subject be? What can that subject be? Let's say history. Let's say it's a college. College name is University of Science, but there is a history subject also, and there's also a history teacher in it. But nobody is interested in studying history. So in the set, so there is a set, that set of history students or students of history. So there is a set, but there's no element in it. That is what is empty set is. Okay. So this is the significance of about set and subset. So what is a universal set? A universal set is a set that is a superset to every other set. So if for a given context, there is one universal context of city population. What is the universal set? It's the set of all people in the city, and set of men, set of women. These are the subsets. So men or women in these subsets, the element has to come from this universal set, which is the set of all people. So this is what it is. There's another representation of set. Right? I talked about this is one representation, curly braces, and inside of the curly braces you write every other element with a means separated by commas. The other notation is set builder notation, and there's another pictorial representation which is called as Venn diagram. In the next video, we will learn about set operations. So most of the set operations, or the next video maybe will be properties of sets. All of them are very self-intuitive. Self-intuitive means you look at the property and you are like, obviously it has to be like that. And even for some properties where you don't get that obvious feeling, those properties can easily be visualized using Venn diagram. So maybe not in this video. In the next video, I will first start with Venn diagram, and then I will also cover set operations. Thank you very much. Hi. Now we will look into different set operations like union, intersection, set difference, symmetric difference, and complement. Some of these operators are binary operators, except one, which is complement. Complement is a unary operator, means the operator that is going to be applied on a single set. But other operators like intersection operator or union operator or set difference or symmetric difference, they are binary because they are applied on two different sets. So you can think of it in this manner. Op is the operator that can either be union or intersection or set difference or symmetric difference. So this op is an operation or operator that can be either union. This is a symbol for union. This is a symbol for intersection. Union intersection. This is the symbol for set difference. This is a symbol for symmetric difference. Okay. And the two operands, the left operand and the right operand, they are going to be sets. So this is operand 1 and operand 2. So left operand 1 and operand 2. So op 1 and op 2, they are sets. Op 1 is a set and op2 is also a set. They are sets. Operands is set and the operations are set operations. Set operations being applied to two sets. Now, what are these operations, different operations? That's what we are going to see one by one. Okay, let's start with intersection first. These are two sets, A and B. Okay, and intersection means that it will return a set that will have elements which belongs to this region. Means if you have set A and set B, the intersection of set A and set B means that you have all the elements that are in both A and B. So such that X not only belongs to A, but it has to belong to B also. Means that A intersection B, when you apply the intersection operation between two sets A and B, then this whole thing will give you a set, or this whole thing is a set. The set operation, when it is applied between two sets, the ultimate result is that of a set. So A intersection B is a set, and the elements of this set are the common elements of A and B. Okay, so A intersection B, the elements are elements of this set. Elements of this set are the common elements of A and B. Common elements of A and B. Okay. For example, if A is, let's say, 1, 2, 3, 4, 5, and B is, let's say, 3, 5, 7, 9, then what is the set A intersection B? A intersection B is a set, the elements of which are the common elements of A and B. What are the common elements between A and B? 3 is present in both sets, 3 is an element in both sets, 5 is an element in both sets. So A intersection B is 3 and 5. 3 and 5. If you just see any arbitrary two sets, this is how you represent two arbitrary sets. And all of these different set operations, whether it's intersection or union or set difference or XOR, symmetric difference, all of these different set operations are actually giving you some region from the Venn diagram. Just look at this. Okay, I will show union here. So let me just draw an arbitrary two sets here. So you can see how many different regions, because of these two sets, how many different regions are possible. One of the possible region is this region, which is the common portion. And to get this element, all these elements, you have intersection operation. So your intersection operation will return a set that has all the elements in this region. Okay. Similarly, all other set operations will give you some of the region from this diagram. The union operation, which is the second operation that we will study. So second operation is union operation. So union operation will return you what area of the means elements from which region, everything. Intersection gives you this portion, right? Intersection gives you this portion, the common region. Union will give you all the elements that is in A or it is in B. It will just return everything. Okay, so what is a union? A union B. A union B. This is equal to all the elements X such that X belongs to A or X belongs to B. So think of this. If your set A contains n elements, and set B contains M elements. Okay, and they happen to be disjoint sets, means there is no sharing area. Okay, let me draw a disjoint set. If the number of elements in A is equal to M and number of elements in B is equal to N, then what is the number of elements of A union B? A union B will have all of it, all of it. So the number of elements in A union B is equal to M plus N. This is in case of disjoint sets. In case the sets are not disjoint, which is this arbitrary sets we are taking, what will happen? Let me take one example and show you. Let's say A is 1, 2, 3, 4, 5, 6, and B is 5, 6, 7, 8. Okay, then what will be A union B? A union B means every element from A and B. So you can just directly write the elements of A and B. Of course, the order does not matter. So you can reshuffle if you want. But the elements are from A and B. But if you just straight away take the elements of A and straight away takes the elements of B, 5 and 6 are going to be written twice because they are common elements. So when you are listing all the elements of A, one time you will write 5 and 6. And when you are listing all the elements of B, second time you will write 5 and 6. So 5 and 6 will be written twice. Okay, and duplicates are not allowed. So let's say you will write all the elements of A, 1, 2, 3, 4, 5, 6, and then all the elements of B, 5, 6, 7, 8. Of course, when you are writing your set in this manner, you will correct yourself. You are not going to write 5, 6 twice because duplicates are not allowed in sets. Means duplicates are ignored in sets. Okay, but you cannot say that the number of elements in A union B for this case, in case when the two sets have some elements in common, they are not disjoint sets. You cannot directly say that this is equal to this is equal to number of elements in A plus number of elements in B, because that will be wrong. You can write this. You can say this in case of disjoint sets, because in disjoint sets, saying this is akin to just listing elements of A and elements of B without taking care if any element is coming twice because of the common element. So this goes fine in case of disjoint sets because there is no common element. When you list all the elements of A, then when you list elements of B, no element is going to come twice because there is no shared elements. There is no common elements. So in this case, this does not hold actually. So in number of elements in A union B is how much? Is going to be 8. You can see for yourself, number of elements in A union B is 1, 2, 3, 8. This is equal to 8. But what is the number of element in A? 6. And what is the number of element in B? 4. So 6 plus 4 has to be 10. So the correct formula in case of A union B to find the cardinality of A union B set is number of element in A plus number of element in B. Then I am going to subtract number of elements in A intersection B. When you subtract it one time, so what happens? I want everything, right? A and B. I want everything. So while listing all the elements of A, you have included these elements. Okay. Now you want every element of B also. So far good. But now again you did this because these are elements of B also. So you are counting this twice. So because you are writing it twice, or when you are calculating the number of elements, you are counting it twice. That's why I have subtracted with A intersection, number of elements in this region. I have subtracted that so as to not count the same element, the common element twice. And this formula is called as inclusion exclusion principle. This is principle of inclusion and exclusion. Inclusion exclusion principle. So this is inclusion exclusion principle. Now I told you about the Venn diagram. So in this Venn diagram, this is about two arbitrary sets. Any two arbitrary sets, that's how it is represented by two circles, and there's going to be one intersection path. But these are the Venn diagram for two sets which are disjoint. From the arbitrary sets, you will come to the solutions. From the arbitrary sets, you will come to the solution. Here also, from the arbitrary sets, I come to this solution. This is a general result, because in case of this disjoint sets, the number of elements in A intersection B will become 0. So this becomes this only. This becomes this only. So this is the general result. Okay, holds for all times. So when it becomes disjoint, then this term is 0. So for a general result, to get a general system, you take two arbitrary sets to get to a general outcome, or so as to get to a um, general result. You use the arbitrary two sets in this manner, and not you don't take these special cases. Like this is one special case where A is a subset to B. These are the special cases. For these special cases, you just fit that special part. Like in this case, if A is a subset of B, then A union B is nothing but B. When A is a subset of B, then A union B is B. Then what is the number of element in A union B? It has to be number of element in B, right? See if this formula holds for that or not. The number of elements in A union B is equal to number of element in A. Okay, no problem. Plus number of element in B minus number of element in A intersection B. And number of element in A intersection B is the entire A. So this becomes number of element in A plus number of element in B minus number of element in A, which is nothing but number of element in B. That's why whenever if you want to come to a solution using Venn diagram, you use these two sets. This is how you will draw two arbitrary sets in Venn diagram. Every set operation will give you elements from some region. You know what intersection will give? You have seen that. What union will give? It will give every elements. Now A minus B. A minus B. It will give those part of A, those elements of A. It will give this region. Those elements of A apart from those elements which are common with B. So A minus B will give you A minus something. So you are not going to return all the elements of A. Some elements of A you are going to remove. If this is your operator, which is minus, and left operand is A, then A minus means that those elements of A are going to be removed that is present in this set, that is present in B. Okay. If this is your two arbitrary sets A and B, then A minus B is this portion. Similarly, what will be B minus A? This portion. Okay. So B minus A is equal to, from the set B, you don't want to include those elements that are in A. So from the set B, from this whole set B, You don't want to include this part. So X says that X belongs to B, but and X does not belongs to A. This is your set difference. Next is symmetric difference. Thank you. Now in this video, let's look at the product of sets. So what is the product of two sets A and B? Let's say we have two sets a set A and a set B. Then what is A cross B? So we have seen different set operations like union, intersection, set difference, set symmetric difference between two sets. And the result of it is also a set. This is also one of the set operation. And the result of this set operation is also a set. Okay. A set is an unordered collection, but the result of it is also an unordered collection, but unordered collection of ordered pairs. So this is a very important point. So A cross B will give you set, no doubt set, which is an unordered collection. Unordered collection. So set of all possible ordered pairs. Set of all possible ordered pairs. Okay. So what do I mean by this ordered pairs? What is this ordered pair? Okay. Like let's say if A is 1, 2, and 3, and let's take B to be A, B, C. Then what is ordered pair? Means that this is equal to a set. This is a set which is each element of it is a pair. Each element is a pair of element. Means each element is a pair X and Y, where X belongs to A and Y belongs to B. Okay, such that X belongs to A and Y belongs to B. So for every A, what are the ordered pairs possible between A and B? 1 and A, 1 and B, 1 and C. Because for every A, it will come, each element of A will come with each element of B. With the in this ordered pair, why it is called ordered pair? Because the first element of this pair has to be from set A, and the second element of this pair has to be from set B. So this pair is ordered pair, but because this is a set of ordered pairs, so okay, let me first write all of the possible ordered pairs. Okay, so all possible ordered pairs is 1 and A, 1 and B, 1 and C, 2 and A, 2 and B, 2 and C, 3 and A, 3 and B, 3 and C, right? So with A has to be paired with each element of B. So you have this. Similarly, 2 is also an element of A, and each element of A has to be paired with every element of B. So 2 will be paired with A, 2 will be paired with B, and 2 will be paired with C. That's what this is. And similarly, 3 will be paired with A, B, and C, and that's what this is. Okay. So a set A cross B set will be equal to all of these elements. And because it's a set, the order is not important. So each element is an ordered pair, but there is no order of it means each element is an ordered pair, but you can't say what is the first ordered pair, what is the second ordered pair. You know what I'm saying. So so it can be 3a, 1a, in any order you can write it. So it's a set, but each element is an ordered pair where first element belongs to a, second element belongs to b. Now you may be thinking that what is the use of it? What is the use of this product of sets? One of the use is in the combinatorics actually, the multiplication rule that we will see very soon. The multiplication rule, the ways of doing things if you want to accomplish a task, and basically there's task T that you want to accomplish, but accomplishing task T means that doing T1 and T2. And let's say there are m ways of doing T1 and there are n ways of doing T2. Then how many ways you can do the task T? Okay. Should I explain multiplication rule right here? See, if let's say you have to accomplish a task T, and to complete task T means doing task 1 and task 2 both, and task 1, for doing task 1, you can do it in m ways. Okay, let's say x1 is one of the way you can do, x2 is another way you can do, and so on so on. There are m ways to perform task 1, and there are n ways to perform task 2. Okay, n ways to perform task 2. Then if you, let's say, if you take any ordered pair means that first element of this ordered pair has to be from T1, and second element from the ordered pair has to be from T2. Then any ordered pair is one way of doing T. Any ordered pair is one way of doing T, right? So if you take x1 y1, I don't know if it is visible or not. So x1 y1 is one way of doing it. X2 x1 y2 is another way of doing it. Another way of doing it. Okay. So in multiplication rule says that if the number of elements in T1 is m and number of elements in T2 is n, then number of ways of doing T is m into n. This is a multiplication rule, because how many ordered pairs you will get is actually m into n. So number of ways of doing T is number of ordered pairs. Okay. And I am taking the ways, T1 to be a set. Okay, this is the fundamental of multiplication. T1, you can think of T1 as a set where each element is distinct way of performing T1, and T2 as a set means task T2. You can think of it as a set where each element is a distinct way to perform T2, and number of ways to perform T is the ordered pair between T1 and T2, ordered pair of T1 cross T2. Okay, number of ordered pairs of T1 cross T2. Okay, I will cover multiplication rule again separately. Just showing that how where it is applied. Actually, this is a fundamental rule of counting. There are two fundamental rule of counting: the sum principle and multiplication principle. Here, the constant is that for T to accomplish, both has to be performed in a sequence. Okay, in a sequence. First T1 has to be performed and then T2 has to be performed. The sequence can change. Let's say there is another task T dash. For T dash, T2 has to be performed first and T1 has to be performed first. The number of ways would not change to perform. Then the number of ways for T to complete T1, T dash or T is same. That is m into n, because multiplication is commutative. But the ordered pairs will not be same. Ordered pairs will not be same. Okay, in to accomplish. So tell me, what are the ways to do T dash? The ways to do T dash would be now y1 x1, this is one way, y1 x2, this is another way, in this manner. Anyways, multiplication rule is not to be covered here. That's a separate topic of in combinatorics. Similarly, there is a sum rule. In sum rule, we will see how the union operation of set comes into play. Okay, so set is, that's why in the very first introduction to a set, I told you that that the sets are very important because building upon set theory, other concepts are derived, and set is very fundamental. Just think about what is a set. It's just a collection. So collection is a very fundamental thing. Anything, anywhere there is a collection, you can think in terms of set perspective. TOC is completely uh, like set membership. TOC can be summed up as a set membership problem. Anyways, so this is your A cross B. What about if there are three sets? What is the product? We are talking about product of sets. This is the product of two set is set of all possible ordered pairs. But what if you have three sets? What if you have A cross B cross C? A cross B cross C. Then this is a set of all possible ordered pairs. No, it is not pairs anymore. Means it's a set of an ordered entity, but that entity is a ordered tuple, three tuple. Actually, the ordered pairs means these ordered pairs are two tuple. You can think what is a tuple now? Right now, I will also relate it with a relational database. So in database, there are different types of database, but relational database is is when you are storing your data as a relation, which is actually a table, and each row is called as a tuple. But each row can be think can be thought of, means it is based relational database is based upon the concept of relation only, and each tuple is actually a k tuple. For example, okay, before I explain, let me just write is a set of all possible three tuple, and I will explain what is a tuple. Okay, so let's see a case of a relational database or relation. If you are very new to the computer science and database is something that you have never heard of, then also you can understand it. Database is a uh, record keeping of entities, like, let's say, look at it. Let's say there is a university, and university is keeping a record of students. Okay, keeping a record of students. Then every student must have some student ID. It's like a register. Student ID, student name. Okay, subjects. Okay, so student ID, let's say first student is Gulam. Okay, and he studies subjects. The subject that he studies is computer science and engineering. And second student name is Moinuddin. Okay, and he studies, let's say, machine learning. Okay, machine learning comes under computer science. Artificial intelligence also comes under computer science. Okay, he is a master of physics. And there is a third student. Let's say his name is Ramesh, and he is a master of mathematics. Oh, sorry, he is a student of mathematics. Okay, and grade is that they are all are toppers, always A plus, A plus, A plus. Okay, so in this case, every row, each row is information about one entity, which entity is a student. So one row contains all the information about Gulam, all the information about this student. Second row consists of all the information about Moinuddin. Third row consists of all the information about Ramesh. And each row is called as tuple. Each row is called as tuple because it's an ordered quantity. Means the first element of this tuple is a number that indicates student ID. But if you just take out the tuple out, if you just take the tuple out, then first element has to be a number. Second element is a string, which is a name of the student. Third element is a string, which is a student subject. Fourth element is a okay, हटा दो, प्लस हटा दो, यही लिख दो, आउटस्टैंडिंग कर दो इसको, ओ ग्रेड. Fourth element of this tuple is a grade. So this is a four tuple. This is a four tuple, something like this: 1 2 3 4. Then you say it's a four tuple if the order is important in this collection, then it's a tuple. So A cross B is set of all possible two tuples. Okay, set of all possible two tuples, where so two tuples means ordered pair. The first element belongs always has to be from A, second element always has to be from B. Similarly, in this case, A cross B cross C, this is a set of all possible three tuple. Three tuple means you had three elements in a tuple, where the first element always has to belong to A, second element always belongs to B, and third element has to belong to C. And all such tuples possible is in your product of sets, you have all such three tuples. Okay, in database, when I will start, I will again explain this. So you can think in database also, each of this is called attribute. Okay, that student ID is one attribute of the student. So this is your student table, then each of these is the attribute of a student. So you can think of every attribute as a set. Then there is something called as domain, that this set will have a domain. Okay, the content of your table is going to be a subset of cross product of each of this set. Means all of these elements are tuples, and they are a subset of cross product of these sets. A set student ID set cross student name set, cross product with subjects, cross product with grade. Okay, let's complete this set of product of three sets. So this is equal to nothing but x, y and z, such that x belongs to A, y belongs to B, and z belongs to C. Okay, so let me take one example to explain. Let's take A to be 1 and 2, A and B, and let's take C to be P and Q. Okay, you will see that the number of elements in A cross B cross C is going to be 8. Actually, the number of elements, the cardinality of A cross B cross C is equal to cardinality of A into cardinality of B into cardinality of C. Every element of A, all possible pair. So for A will be connected with, one will be connected with A, then A with P and A with Q. So one A and P is one three tuple, and then one A and Q is another three tuple. Similarly, one will be connected with B, and B will be connected with P and Q. Another two three tuples are 1 B and P. 1 B and Q. Likewise for 2. Okay, so 2A and P, 2A and Q, 2B and P, 2B and Q. Okay, so as you can count the number of elements 1 2 3 4 5 6 7 8. So this is equal to number of elements in A is 2 into 2 into 2, which is equal to 8. So in general, so I have taken two cases, product of two sets, and I have shown that product of two sets is a set of all possible ordered pairs, which is a set of all possible two tuples. Product of three sets is set of all possible three tuples. Similarly, you can, let's say there are k sets. Then product of k sets is what? Set of all possible k tuples. Okay. And what is the number of elements in the product of k sets? It is equal to the cardinality of each set product of the cardinality of each sets. So when we have product of sets, the cardinality of the product of set is equal to just product of their individual cardinalities. I don't have to. I don't think it needs a proof. It's a straight. But let me show it. Let's take only. Let's take first two sets, and it will be easy for me to explain. Let's take two sets A and B. What is happening is that if this is your set A and this is your set B, then every element of set A is connected with every element of set B, right? So if let's say set B has m elements, n elements, let's say set B has n elements, then A has m elements. Then for every element of A in the ordered pair, in the set of all ordered pairs, each element is each element of A is adding n elements. Okay, each element of A is adding n elements. So this is your first element, let's say A1. So A1 is adding n elements to the set of ordered pairs. M elements, sorry. Similarly, A2 will add, because then now A2 will be connected with each element of B. So A2 will also add n elements, and so on. All the m elements are going to add n elements. So what is the ordered pair? It is n plus so on m times, which is equal to n into m. Okay, which is equal to m into n. Now, if there are three sets, if there are three sets, let's say there is another set A, B, and C, and C has, let's say, P elements. Now, your three tuple, your three tuple is going to be something like this, where these two, this is the this place is for element of A, this is place is for element of B, and this place is for element of C. Now you know that you already know that set of all possible ordered pairs means this part is going to be m into n. Let me just replace it with m into n. What I mean is that this is my A cross B. Okay, so of course this is going to be, let's say, one ordered pair A1 A2 and A1 A1 B1. A2 B1, A2 B2. Okay, don't take it as a set. Why I'm doing so? Because then it will, I will explain in a while that why I'm not doing it. I am just saying that your triplet is going to be like this: A1, B1, and something from set C, A2, B2, and something from set C, A3, B3, and something from set C, and so on, so on. How many such is possible? Means I am not filling this part. I am just looking for distinct these. So how many such? There are m into n such, right? Now to include this, we have to pick it from here, and for each of this, you have p choices. You have p choices. So it becomes in a similar manner. It becomes what? For first one, you have p choice. For second one, you have p choice, and so on, so on. For m into nth one, you have p choice. So the number of elements become what? P plus, so on, p, which is equal to m into n into p. Okay. What about the product of four sets? Similarly, for product of four sets, what you will do? So for four sets, this is like principle of mathematical induction. If you were studious in your 11th and 12th, you would have understood this already, that we can apply mathematical induction to get the result. But I don't think that you were studious, just like me. So if it was four sets, then you know that there's going to be four tuple. There's going to be four tuple. Okay. So you know about, if you just take uh, if you just consider this region up to this, all the distinct elements in up to first three only, then you know that how many are those: m into n into p. And then for each such m into n into p, you have, let's say, for if you have a into b into c into d, if you have four sets, and let's say d has cardinality d, then for each such you have d choices, and then the cardinality of a cross b cross c cross d is nothing but m into n into p into d. Okay, so it's okay. Now let me just directly write. I have proven. So let's say if you have set A1, set A2, set A3, so on, so on, set AK. Okay, then this is the product of such sets. What is the cardinality of this? This is equal to cardinality of A1 into cardinality of A2 into cardinality of A3 into cardinality of A4 into so on, cardinality of AK. This is the result. Okay, so product of sets is over. In this video, I'll start relation. So what is the relation between two sets A and B? So let's say there is a relation R between set A to B. Okay, so any relation between two sets is a set of ordered pairs. Okay, any relation R between two sets, say A and B, are set of ordered pairs formed from set of ordered pairs formed from elements of A and elements of B and elements of B. Like for example, let's say just I am taking just one arbitrary set A that has the elements 1, 2, and 3. Okay, and there is another set B that has the elements as ABC, ABC, and I am just taking one set, which will a set of some ordered pairs, where the first element belongs to A and the second element belongs to B. Let's say 1A and 1C, 2C, 3B. Let's say I have taken this set. Then this set is what? This set is said to be a relation. We know that A cross B is the set of all possible ordered pairs between A and B. So any relation is a subset of the cross product of set. Any relation is a subset of cross product of sets, cross product of A cross B. So any relation between A to B, this is how we represent a relation, that R is a relation from A to B. So if R is a relation from A to B, then it is a subset of A cross B. Because if it's a relation, then the elements in the relation is going to be an ordered pairs. And A cross B, the elements are all possible ordered pairs. So anyways, you can think of, the analogy in the world of ordered pairs, set of all possible ordered pairs is A cross B. So you can think of A cross B, that A cross B as a universal set. In this context means in the context of ordered pairs, A cross B is a universal set. What is a universal set? The set that has all the elements in a given context. So in this context of ordered pairs, what is the universal set? A cross B. So universal set is A cross B. Okay, so any other set whose elements are the ordered pairs only, they are called relation. So any relation, the elements of a relation will come from the A cross B only. That's why any relation from A to B is a subset of A cross B. So the definition of relation that I have written here is a relation R between two sets are set of ordered pairs formed from elements of A and elements of B, right? Set of ordered pairs. So A cross B itself is one relation only, because A cross B is also a set of ordered pairs. It just happens that it has set of all possible ordered pairs, but ultimately, because it's a set of ordered pairs, so even the cross product is also a relation. Okay, A cross B is also a relation. A cross B is also a relation. How do we take these ordered pairs in a relation? Means if 1 comma A belongs to R1, okay, what does it mean? It means that 1 is R related with A. 1 is R related with A. So a relation from A to B means that how the elements of A is related with the elements of B. So in this relation R1, 1A, 1C, 2C, 3B, how the elements of set A are related with elements of set B. So 1 is related with A. Okay, 1 is related with C. 2 is related with C. 3 is related with B. Okay, you can also think of the relation R as some sort of a rule. How you will relate A and B? Are going to relate it by rule R1. Okay, so by this rule R1, what are the elements that are related? 1 is related to A. 1 is R1 related to A. Okay, 1 is R1 related with C. So by R1 rule, 1 is not related to B. So 1 comma B does not belongs to R1, or 1 is not R1 related with B. Okay, how do you represent a relation? This is one way to represent a relation, that you write all those ordered pairs, all those valid ordered pairs, or you can represent it in this manner. This is the diagrammatic representation. Okay. The another way to represent is using a matrix also. We can represent a relation. Now, if one is related with A, if one is R1 related with A, then I write 1. And if it is not related, then I write 0. So 1 is related with A, then 1. If it's not related, then 0. 1 is related with C, yes, so it's 1. 2 is related with C. 3 is related with B. Okay. So this is about relation. Thank you. Just like in different set operations like union and intersection, we saw that commutative and associative laws, whether they hold or not. Similarly, in this video, let's look whether the product of sets obey commutative laws or not, or product of sets obey associative law or not. Actually, they don't obey, and this is quite obvious. I'm going to explain it, but it is also quite obvious because A cross B is an ordered pair, a set of all possible ordered pair. But in the ordered pair, your first element is from set A, the second element is from set B. Now, if you keep the same set and just interchange the position, what you get is A P cross A. And so, but anyways, these two ordered pairs with interchange positions, that is x1 and y1, is one ordered pair. The interchanged, you just interchange the position, then these two are different ordered pairs. Okay, in ordered pair, order matters. It's not about the same elements. It's about what is the first element, what is the second element. Order is important in the ordered pairs. So these two are not equal. These two are not equal. So if these two are not equal, then obviously A cross B is not equal to B cross A. A cross B is not equal to B cross A. Right? What is A cross B? A cross B is equal to an ordered pair of A and B such that A belongs to A and B belongs to B. Okay. Now to this set only, if you make B as the first element of the ordered pair and A as the second element of the ordered pair, means for every element in A cross B, if you are interchanging the positions of ordered pairs, interchanging the position of elements in the ordered pair for every such ordered pair in A cross B, then the new set that you are getting is nothing but B cross A. So B cross A is equal to this. Just for every ordered pair, you are just interchanging the positions. So A belongs to A and B belongs to B. Okay. And you know that these two, any two such ordered pair are not going to be equal. And so A cross B and B cross A can never be equal. So A cross B is not equal to B cross A. It's not that they can never be equal, but if A and B, if sets A and B have any one element which is not same, if either one of the element in A cross B, if either A or either B is phi, in that case they can be equal, because then you are not getting any element in the empty set to pair with. Means A cross phi is equal to phi, because you cannot pair the elements of A with any element in the empty set, because there is no element in the empty set, so you are not getting anything to pair with. So A cross phi is phi, or phi cross A is phi. So if any of A or B is phi, okay, if A is equal to phi or B is equal to phi, or B is equal to phi, then A cross B is equal to B cross A is equal to phi, right? Other than that, they will always be not equal to each other, except also when A and B are equal. If A and B are equal, then it is more like A cross A. So you can add this condition, that condition here, that if A is equal to B also, then A cross B is equal to B cross A. Okay, so this is it. So it's clear that product of sets are not commutative. Product of sets are not commutative. Product of two sets are not commutative. Product of two sets are not commutative. As a rule, they are not commutative. Means for special cases when A is phi, special cases when A and B are actually the same set or equal sets, for those cases the product is commutative, but that is a special cases. As a rule, they are not commutative. Actually, apart from this, they are always going to be not equal. So product of sets are not commutative, and A cross B equals to B cross A only when A is equal to phi or B is equal to phi or A is equal to B. Okay, let's look the associative law, whether the product of set obey the associative law or not. What will this give? This will give a set of ordered pairs, because this is one set, let's say S1, and this is another set S2. Of course, S1 is in itself a set of ordered pairs, and then this is a cross product. So this will give you a ordered pairs where the first element is an ordered pair and the second element is any element from set C. Means the ordered pair will be like this. First element is an ordered pair, and an ordered pair is paired with the element of C. Okay, so this is A, B and C. So A belongs to, or more like, ordered pair AB belongs to A cross B and C belongs to C. Okay, and this is a set of ordered pairs, because this is a cross product. The element of set A is being paired with an ordered pair. In the RHS, if this is your RHS and this is your LHS, in your LHS the first element is an ordered pair, in your RHS the second element is an ordered pair, so definitely they are not same. Okay, B and C and A, where A belongs to A and B and C belongs to B cross C. Actually, when it comes to product of sets, I can make it as complex as possible. Okay, like in this case, there is an ordered pair with an element of the set. I can just say that my C is also a set. Set can have anything. Maybe C is also a set of ordered pairs. Then what is the net result of this operation would be that an ordered pair is being paired with another ordered pair. Whatever the case it is, will not be associative. They will not be associative. Okay. So product of sets are not associative. Okay, I will explain the complexity again, but the result I'm going to write it right now. And let me take some complex examples of product of sets before getting into relation. So product of sets are not associative. Okay. 1, 2, 3. B is equal to 4, 5. AB X, Y, Z. First of all, the number of elements in A cross B will be 9. So number of elements in A cross B will be number of element in A into number of element in B, which is equal to 3 into 3, that is equal to 9. Now let's list all those elements. So, or let's just write the set A cross B. Each element is going to be paired with every element. Every element of A is going to be paired with every element of B. So as you can see, this ordered pair will be 1 and 4, 5. Okay. Then 1 and AB. Then 1 and XYZ. Okay. Then 2 and 4, 5. Similarly, 2 will be paired with each element. So 2 and 4, 5. So here in B, every element is an ordered pair. Okay. No. In B, these two elements are ordered pair, and this is a 3 tuple. In a set, you are just having distinct elements. Those elements can be anything. Okay. In a set, you can put a cat and dog. A cross B will give you a set of ordered pairs. An ordered pair is something where you have two elements in order. And what are those two elements going to be? They can be simple a number, they can be it themselves an ordered pair, they can be 3 tuple. One of them can be 3 tuple, both can be 3 tuple. I can just add one element in A which is a 3 tuple. Then that 3 tuple and an ordered pair will be paired into an ordered pair. Okay. So you just need to know that what is happening is that each element is being paired with every element of the other set. Means the second set, means if this is A cross B, then elements of A is being paired with each and every element of B. Now the element of A can be anything. The element of A itself, that element can itself be an ordered pair or a 3 tuple or any k tuple. Okay. The in elements of B can be anything, but then these two things are being paired. Enough of it. I am going to just explain, write this and end this video, and in the next video I will start relation. So 2, 4, 5, 2, A and B, 2, XYZ. 3, 4, 5, 3, AB, 3, XYZ. Okay. Let's take one more element in A, just for the sake of doing it. Let's take this also some k tuple, some ordered pair. Let's say I am taking it as C and D, and let's take some 4 tuple, PQRS. Okay. Then the CD will be paired with every element. So as you can see here, this is an ordered pair in which each element is an ordered pair. Now let's end this video here. In the next video, I will start with the relations. Finally. Hi. So we know what a function is. A function is, if a function is from A to B, then elements of A is uniquely mapped to elements of B. Okay? Such that all the elements are uniquely mapped to element of B. Now, because of this property, in most areas, a function is perceived as something like this. That this is a function, it will take some input. Okay, and input is given to a function, and based on the input, this function will give you some output. Okay, this is how at many places how function is perceived as, that a function takes an input and it gives an output. Now, a function is a function is a special type of relation from set A to set B. So this input would be coming from, if this function is from A to B, then this input will come from set A, and the output is any element from set B. Okay. Now, in different computer subjects, in computer science subjects, we will see many things which are actually functions. For example, in database, we will see that some of the attributes functionally determine some other attributes. There, in database, you will see functional dependency, something called as functional dependency. Now, about functional dependency, that we will see in the database subject in computer science, but I will just give you a little insight. In database, there's a relational model. In the relational model, the data is stored as tables. You have, let's say, student. Student may have a student name, okay, and maybe school name. Okay, we are talking about, let's say, a government registry of schools all over India. They have a database they have a table that stores all the school names. So leave the student, make it student school ID. School ID is school name, branch, and address. Okay. So for every school there will be a record. So one record will contain about every school. Its serial ID, let's say 1. School name, let's say St. Michael's High School. Okay. And the branch, let's say Bihar branch. And then there's going to be some address, say Digha. And then there is another school which is Don Bosco and branch Delhi, and address I don't know if there is such a place or not. But what I am saying is this, that before while creating the table, the database designer will specify some functional dependencies. And what are the functional dependencies? It's like, if you know what the school name is, then school name and branch. If you know a school name and branch, then the address has to be Digha. So if there are other columns maybe, so if this if this record happens to come again, if St. Michael's High School of Bihar in Digha, let's say for some other information, if they are more than one row, if after some time also, if your school name is St. Michael's High School and branch is Bihar, then it means that address will be Digha. This is what the database designer have to specify while creating the table, and so the right information is being entered every time. A caution is there. So this is one of the integrity constraint. Functional dependency is one of the integrity constraint, and anytime you insert any value, anytime you insert any new record, that record must satisfy all the integrity constraints. So that record must satisfy. It will check that okay, if a school name is St. Michael and branch is Bihar, then the address has to be Bihar. So what it means that the school name and branch is uniquely mapped to address. A school name and branch is uniquely mapped to address. Means that for every combination of value for school name and branch, for every combination is uniquely mapped to the address. So there are many addresses, but every combination is mapped to exactly one. So that's why it is called functional dependency. Okay. So this is the application of function in database. Similarly, in probability, what happens is, you know a little bit about probability, even if means you have passed 12. So in probability, for a given experiment, there is sample space. Sample space is set of all possible outcomes. Now, what you want to find is the probability of any event. Okay, so an event is any subset of sample space. Now, this is how we look at probability as P is a function. So in probability, you write like this: probability of any event E. So this is a function P. Function P is a function. Probability is a function that takes an input, an event, and it gives an output. That is any number between 0 and 1, maybe 0, maybe 1. 0 for impossible event, 1 for sure or certain event. So any number from 0 to 1 is possible. But it will be any one number, means it will be a unique value. So we say that a probability is a mapping. Probability is a mapping, or probability is a function from this set to this set. So omega is sample space. So basically, actually, instead of all events, or power set of sample space, very simple. Power set of sample space. So power set of sample space is nothing but set of all events. So individual element of power set of sample space is in event. So this is your set. Okay, this is E1, E2, E3, so on, all possible events. So probability is a function that maps, uniquely identifies or uniquely maps any event to a number from 0 to 1. Okay, so this is another area where a concept of function is used. Any other place where functions are used? Okay, in programming languages, you know that programming language like C programming language, it is basically, in nutshell, it is one function calling another function. So why it is called function? If you look at any declaration statement for any function, it is like return type, function name, and then it will take some arguments. This is more or less what a function, how a function is. So this return type is because when you give these arguments are nothing but input to a function, and function will return something, which means nothing but the output from a function. So the fact that a function from A to B, the elements of A is uniquely mapped, because of this definition, this is how a function is generally perceived. Let me take an example of a function. Let me take a set A and set B, and let me show how a function is there. Let's say set A is, let's say set A is 1, 2, 3, 4, 5, and you have a set B that is 1, 2, 3, 4, 5, 6, so on till 25. Okay, and what is the ruling condition? So if function is a f that is from A to B, okay, and what is it? Such that f of x is equal to x square, then this is a function. So how every element of f is mapped? So how do we write? What is the explanation? What is this? So look at this symbol. This is how we explain this template. Okay. Here what comes is your input, and using this formula you get the output. So I can, so it's like you give x, function will, now function will use this f, the rule on this x. You give x as an input, function will use the rule on this x, and what the output is x square. So the rule is x square. So f of x means x square. So what is f? If f is a relation, you know that. So f is equal to 1 and 1, 2 and 4, 3 and 9, 4 and 16, 5 and 25. This is your f. Now if the question is that what is, if it is asked what is f2, then what is f2? It means that 2 is the input, and now you will apply the rule f on this 2. So by applying rule f on this 2, what you get? You get 4. Okay, and so this is a representation. So f2 is equal to 4. Similarly, what is f3? f3 is equal to 9. f4 equals to 16. f5 equals to 25. Let me say there is another relation on A to B only. Okay, and how elements of A and B will be related is A belonging to A and B belonging to B. A is related to B if A is a factor of B. Okay, so this is your set. This is your set A and B. This is a function that is defined on A to B, and this is one relation that is defined on A to B. So what are the ordered pairs of R will be? So 1 is a factor of everything, right? So 1, 1, 1, 2, so on, 125. Then 2, 2, 2, 4, 2, 6, 2, 8, so on, 224, right? 3, 6, 3, 3, 3, 6, 3, 9, so on, 324, 4, 4, 4, 8, 4, 12, so on, 424, and then 5 1, sorry, 5 5, 5 10, 5 15, so on, 5 25. So this is your relation R. Now if I ask you what is R1, what is R1, then just like if you see at a function, for any input that you give, you are getting just one output. Now you are not getting just one output. Okay, so R1 is equal to 1 also, 2 also, 3 also, 4 also, so on 25. Similarly, for R2 you will get more than one output. For R3 you are getting so many outputs, right? I mean 8 outputs, looks like 3 as a 24. Similarly, for 4 you will get 6 outputs. For 5 you will get 5 outputs. That's why carry forward on calculus we will stick to the function. Okay, now in the next video we will see the different types of mappings on a function. Thank you very much.